0, 3 count pairs with XOR in a range. So for this problem, we are giving an array numbers, and we are also giving two integers, low and high. And basically, we want to find all the XOR pairs from I to j. So I gonna less than j, gonna less than the length of the nums, and I gonna be more than or equal to 0. Yeah, basically we want to find all the pairs. So if the XOR of each pair, so for example it is 5, it is inside the range, so we're gonna code it by 1. And in the first example, also we're gonna return a 6 because all those values are gonna be inside the range from low to high inclusive. Yeah, basically this is a counting problem. We want to count all the XOR cases. If we use brute force, definitely it's gonna be O(n) square. It didn't work. Yeah, so we're gonna use some easy ways to solve it, and the easiest way is by using the 0, 1 trie. Yeah, so let me just make a drawing to explain what is the meaning of the problem. Yeah, let me just start from beginning. Let's just imagine we just have some numbers inside of the array. So currently, we're gonna prepare the nums array. Inside of the nums array, let's just prepare some numbers. I'm gonna prepare. Yeah, maybe this example, it is also okay. So in the first example, I'm gonna prepare the first example. Yeah. So this is my root node, and this is my trie. I'm gonna start it from here, and the first number is 1. Yeah, so normally I'm gonna prepare 4-bit. The 3-bit is also okay, but I'm gonna prepare 4-bit for easily to explain the problem. Yeah, so I'm gonna starting from the highest bit to the lowest bit. Yeah, so for the first one it is 1, so it's gonna be 0, 0, and 0, and the last bit is gonna be 1. Yeah, so this is just the insertion. So as I'm going to count the number of possible pairs. Yeah, so while I'm preparing the node 0, 1 trie node, I'm preparing the counter as well. So for example, this is 1, 0, 0, 0, 1, and for each node I'm going to prepare a counter. So for this 0, the count is going to be 1, and this 0, the count is going to be 1 as well. And yes, here going to be similar. Yeah, this means I prepared the first number. While I insert a node, I know this node is going to be the first time appeared here, so it's going to be 1, and similarly for others. And then I'm going to insert the next number, which is going to be 4. This number 4. Yeah. So what about number 4? It's going to be 0, 1, 0, 0. So this is a 0. So I'm going to update the counter. So from the beginning, it is 1. Now I'm gonna update it to 2 because I have another number which is 4, right? Yeah. So the first one is 0, and then I'm gonna insert a 1. 1 gonna be here, and the counter gonna be 1, and I'm gonna continue. It's gonna be 0. The counter gonna be 1, and 0 here. So the counter gonna be 1. Next, I'm gonna insert this number on 2. Yeah, so this is just to simulate what is the insertion of the trie. Yeah, so we're gonna just include a counter. So for each of the node, we're gonna not only have the value of the node, we also have a counter. Yeah, and then it's gonna be 2. 2 gonna be something like 0, 0, 1, 0. Yeah, so this is a 0, and this is a 0, and we're gonna update the counter. So here gonna be 3. And this counter gonna be 2 because it is a 0, 0, and then it's gonna be 1. So this node gonna be a 1. So the counter gonna be 1, and the last one gonna be 0. Yeah, and here gonna be 0. So the counter gonna be 1. Yeah. So this is how to simulate the insertion. So this is how I gonna insert all the values into a trie. We are not insert the values like 0 and 1, but we also insert a counter. So for each of the node we have a counter. I will explain why we're going to use this counter, because this counter really helps us to solve the problem, to count all the possible pairs. Yeah. Now I'm going to explain why we can use this counter to solve the problem. Yeah. So for this 7, for the last number 7, before insert it, I'm going to first check it, how many pairs. So this is really important for us to understand why we're going to solve the problem like this. Yeah, just imagine we just insert all those three binary numbers 1, 4, 2 inside of the trie, and then we want to insert the 7. But before inserting this 7, we want to count how many pairs first, and then we're going to insert it. Yeah, so the idea is that we want to try to find all the possible pairs, because for this 7, maybe I have a pair of 1, 7, maybe I have a pair of 2, 7, and maybe I have a pair of 4, 7. Yeah, for the 7, maybe I have 3 pairs meet the conditions, but I want to count it first, and then I insert it. Yeah, this is just to avoid the duplicate numbers. Otherwise, if we insert all the numbers first, then we're gonna search. We're gonna find the duplicate pairs like 1, 7 and 7, 1. Although this is okay, but for the final result, we're gonna divide it by 2. But we don't want to do it like that. Yeah, so we want to avoid the final result divided by 2, and we want to avoid 2 passes of the for loop to check. We're gonna only use one for loop to check the result. So this means before insertion, we're gonna count how many possible results. We've already counted, so we don't need to check again. Yeah. Now for this 7, before we insert it, we're gonna count how many possible cases. And for this low and high, we're gonna prepare a limit. So normally we're gonna check the value from low to high. It's gonna be really difficult. But what if we just check a limit? So the limit is gonna be the high limit and the low limit. We're gonna prepare a high limit. High limit is gonna be this high plus 1, so it's gonna be 7. Because for our check, while we are checking the pairs, it's gonna always be less than the limit. We will not try to use some values which is less than or equal to limit, because less than limit is just easier to solve. We're gonna use some value less than this limit at 8, and then we're gonna use some value less than this value low. Yeah, so the low gonna be 2. So 2 gonna be, if we use 3 binary numbers, it's gonna be 0, 1, 0. Yeah, if we use 4 binary numbers, it's gonna be 0, 1, 1, 1. For the high, it's gonna be 7, and for the low, it's gonna be 0, 0, 1, 0. It's gonna be low. So the final result is gonna be, maybe a function. Gonna be the function of the high minus the function of the low. It means all the values less than 7 minus all the values less than 2, and then we're gonna have all the values between 2 to 6 inclusive. Yeah, so this is the basic idea. But at the moment, let me just use this 7 to explain, because 2 gonna be exactly the same. So here we're gonna use this high limit. It's gonna be 7. We want to find all the numbers which is less than 7. Yeah, but how can we find it? Yeah, so this 7 is will just happen to be a 7. It doesn't matter. Maybe this is a 6 or 8. It doesn't matter. But this number 7 is according to the high plus 1, which is going to be 7. Yeah, but it's just like a coincidence for us. The last number is a 7, but it is okay. Yeah. So for our last number, so this is our number for our last number, which is 7. Yeah. And for the binary representation, it is also something like 0 or 1, 1, 1. Yeah. Now, how can we count it? We're going to check the first bit for the limit. So for the first bit for the limit, which is 0. Yeah. So for the first bit, which is 0, and for our number, which is also 0, as you can see, this number is also 0 for the highest bit. Yeah. And for this 0 XOR this bit 0, so what's the result? So it is a 0 because it is the same bit. 0 XOR 0, it's going to be 0. So this means this bit is okay. Yeah, so while we are checking this number, if it is 0, so for the number, it must be 0. It cannot be 1, because if it is 1, it is too big. We're gonna stop checking because it is not possible. And likely for us, it is 0. Yeah, as you can see, this is 0. Normally we need to find a number. If we were to find this number XOR some number less than and equal to this 0, so definitely it must be 0. It cannot be 1, because 0 XOR 1 gonna be 1. 1 gonna be more than this bit. Yeah, we're gonna compare bit by bit. Yeah, now let me just continue. Because this is 0 and this 0, this means 0 gonna XOR at 0, so this means we can continue. Yeah, but currently, do we need to count this 3? We don't need, because we are not sure. We are only sure the first bit 0, the highest bit 0 equal to the highest bit in the 0, 1 trine. It is okay, but we are not sure how many of them. Yeah, so we're gonna continue to check. So this is the current node gonna equal to current node dot children. Yeah, so from the beginning, this is the current node. It is here. It is at the root, and now the current root, the current node gonna be at this 0. It means it is okay. I can go to this node 0. Yeah, and now what about the next bit? Yeah, so the next bit is 1. So the next bit is 1, but for our number, it is 1. Yeah. If this number is 1, what are we gonna do? Definitely we want to find a 0, because 0 XOR 1 gonna equal to 1, but 1 XOR 1 gonna equal to 0. Yeah. So which one? So normally for this situation, which one we need? Yeah, because this is a 1, it can be a 1. 1 is also okay. We just don't need to count it, because we don't know how many of them. Yeah, because this bit equal to this bit 0, 1, 0, 1, it is equal. But after that, we don't know. We don't know which one is bigger. It is still okay for us. I mean, by this n, XOR some number. This number gonna inside the trie. Yeah, if it is 1, still okay. We're gonna continue. But for us, if we want to count it, we actually want to find a 0. Because 0 XOR 1, actually we want to find a 1. I'm sorry. Yeah. So actually we want to find a 1, because 1 XOR 1 gonna be 0, and this 0 gonna be less than this bit. If it is less than this bit, we're gonna count it, right? Yeah. Now from this 0 here, yeah, now from this 0 here, we want to find a bit 1. Yeah, so this is a bit 0. We want to find a bit 1, because this one XOR or n gonna be 0, and then we're gonna count it. Yeah, so this means from here we can count it. If we choose this branch, because this is 1 XOR this 1, it's gonna be 0, and 0. Yeah, and this number gonna be 0, 0, something, something. Definitely, it's gonna be less than 7. Yeah, 0, 0, something, something gonna less than 7. We are sure. Now we're gonna have a count, and from here we're gonna check the counter of this node. It's gonna be 1. It means from this node and all of them, we're gonna count it. So currently our result gonna, this is our result gonna equal to 1. But this right branch has already been finished. It is okay. But what about the left branch? So we still need to continue to check the left branch. Yeah, because the left branch is still okay. 0 XOR 1 gonna be 1. 1 and 1 is gonna be the same bit. Yeah. So this means it is still okay. So now our current node gonna be here. Yeah. Now what are we gonna do? We're gonna still need to check the left and the right. Yeah. So this is our current node, and then we're gonna check the next bit. So the next bit from the limit, highest limit, it is 1. Yeah, and for our number, it is 1. So this means if it is 1 XOR 1, it is 0, it is okay. So this side, it is okay. This is 1. Yeah, so we're gonna plus a 1. Now this means this branch at the right side has already been finished. But we still need to go to the left side, so our current node is gonna be here. Yeah, because 0 XOR 1, it's gonna be 1, and yeah, we just need to continue on to tag. Yeah, so what about the last one? Yeah, so this is 0. Now we're gonna shift to the last node. Yeah, so our last node is 1. This means we need to find this is 1, and this number is also 1. We need to find 1. If it is 1, it is okay, basically. Yeah, because 1 XOR 1 it is 0, we're gonna count it. Luckily for us, this is 1, because 1 XOR 1 is gonna be 0, so we're gonna count it. Yeah, so this means we're gonna still need to count it. Yeah, so how many pairs in total? Because we've already finished coding all the bits 1, 2, 3, 4, and how many pairs? 1, 2, 3. It means all those pairs, like 0. Yeah, because this 7 gonna be index 3, like 0, 3, 0, 3, 1, 3, and 2, 3 gonna meet our conditions, because currently we are only checking the index 3. So it means 0, 3, 1, 3, and 2, 3 meet the conditions of less than 7. And similarly, this is the 3 pairs. And similarly, we're gonna check how many pairs are less than 2. And we didn't find any pairs less than 2. It is 0. So 3 minus 0 is gonna be 3, and 3 gonna be our final answer. Yeah, but for this case, it is okay. But let me just use another example. So, for example, our limit is still 7. So this is our limit. So this is our highest limit. It's going to be this high plus 1. It's going to still be 7. But for our boundary numbers, instead of all those numbers, I'm going to prepare an edge case. Maybe it is 15. So basically, it is 1, 1, 1, 1. So this is my root. And then I'm gonna have the boundary bit of 1, 1, 1, 1. Yeah. So what's gonna happen for us is that the first bit is 1, right? Yeah. And basically we want to find a number which is gonna be less than 7. Yeah. And if our number maybe it is yeah, let's just use an example, maybe 0, 0, 0, 1. So this is our number. So this is our current number. So this is the high limit. Yeah. So for the first bit, actually, this is 0. And for our number, it is 0. Definitely, we cannot make a 1 because 0 XOR 1 gonna be 1. We want to find a 0. And currently this is root. I want to find a node 0, but there's no 0. This is 1 because this is 1. We don't have any 0. If we have it, it is okay for us, but we don't have it. How can we deal with this case? So this means if we find the root, maybe the current dot children. Yeah. If the current node has no children, if there's no current node, so for example, this is a root, and root gonna shift it to the current. If the current is none, if this is none at the right side, so we're gonna stop it. Yeah, because definitely all those values will not meet the cases for our checking for this number 1 with this number 11. It didn't meet the it cannot combine any pairs, so we're gonna stop it. Yeah. I think I've already prepared all the edge cases. Now let's just start coding. The coding is gonna be a little bit long, but I think it is still okay if you understand the problem. Yeah, so everyone has different writings. So for me, I'm gonna use a try node and try. And for the slots inside, I'm gonna define some variables. This is just for speeding up a little bit. So I'm gonna prepare the children and a counter inside of my try node. Now I'm gonna define the try node. So the self.children gonna equal to an array. So the length of the array gonna be 2, and inside it's gonna be none. And I'm gonna define the self.counter is gonna be 1. Yeah. So this is the try node. Now we can define the try. So similarly, let me just copy the code. we're gonna define the root first. Self.root gonna equal to the try node, and then we're gonna need two variables as I explained earlier. So the first step is that we're gonna need to use insert, because we want to insert the binary numbers inside of the try. It's gonna be this number. And secondly, we need this search, because for search we need to find all the possible results. Yeah, so currently I will give a pass at the moment. Now let's just finish the main function before we just try to solve how can we write this insert and search. Yeah, because this is the main part actually. But let's just finish here. So we're gonna prepare a try. It's gonna be equal to the try class, and then we're gonna check all the possible numbers. So let me prepare a result. It's gonna be 0. Yeah. Now before insert any numbers, we're gonna check it first. We're gonna code it first. It's gonna be equal to try.search, and inside I need to use this number, and I needed to use a limit. Yeah, but for this limit, it's gonna be high plus 1. As I am going to find all the numbers which gonna be less than high. This is why I gonna need to use a high plus 1, and minus try.search, and inside, we're gonna still use this number. Yeah, but it's gonna be low. This means all the numbers are gonna be less than this low, and after that we're gonna find all the numbers between low to high inclusive. Yeah. So after search, we're gonna insert it. So in this way, we don't need to have the duplicate calculations. So try dot insert and with the number. Finally, we're gonna return the result. Yeah. Now, what's left behind is how can we finish this insert and search. So the insert is gonna be easier, as I explained. We just need to insert, but with a counter. Let's just prepare a current node, because we're gonna always insert from the root node. So the current node is gonna equal to the self.root, and then we're gonna check the binary numbers. We're gonna insert 1 bit by 1 bit. So the highest bit I'm gonna set it as 15, because the highest number is 2 times 10 to the power of 4. So basically it's gonna be less than 2 to the power of 15. It's gonna be okay. Even use even use XOR calculations, it should be okay. 15 is big enough. So I'm gonna start in from the highest bit, and here I'm gonna prepare a calculated value. So this value is just a bit. It can be 0 or 1. So currently I'm gonna use this x. I'm gonna right shift I bit and add 1. I'm gonna check if this bit is I'm gonna just insert it into the try. So if current.children.n, this n can be 0 or 1, is a noun. If it is a noun, I'm gonna prepare a try node. Yeah. So current.children.n will not equal to noun. It's gonna equal to a try node. Yeah. So I'm gonna prepare this try node, and then I'm gonna insert it. So current.children n. So the current, I'm gonna shift to the current node. Current gonna equal to current.children with this n. Basically, it's gonna be pointed to this try node. So after that, I'm gonna prepare the counter. So current.children n. Yeah, let me think about it. This is the current gonna equal to current.children with this n. and the current dot children n, I'm gonna dot count, gonna plus equal to 1. Yeah, I think it should be okay, but yeah, let me just check if it is okay. So currently I will not use the search, I will just use insert. I just want to check if the insert is okay. Yeah, let me just run it. It didn't work. I think it's gonna be current.count, because current has already pointed to this try node, and I just needed to update the counter. Yeah, let me just run it like this. Yeah, now as you can see, it seems it is okay. At least we can run the program. Yeah, I think I fixed it. Because for this the current, this is our last node, and for this node we just needed to update the counter instead of its children. Yeah. Yeah. Now, what's left behind is that we need to try to finish the search function. The search function actually is going to be the main function. Let me uncomment this one, and let me copy some code from the insert because it's going to be similar. Yeah, let me just copy all of them. So first of all, I'm going to prepare the current node. It's going to be the root node, and then I'm going to check the highest bit. Yeah. So first of all, for this number, yeah, here I don't need it. So first of all, I'm going to prepare my number. The highest bit of my number, it can be 0 or 1 for this. And I need to check the limit first. So the limit going to be, let me just define a limit. So this limit is going to be high plus 1 or low. So this is going to be the limit. Yeah. So limit going to be right set I and 1. If the highest bit of the limit is 1, this means so if the highest bit of the limit is 1, so this means we have to choose it. Yeah, let me just use example 7. So if this highest bit is 1, and for our number, if the highest bit is 1, it means we have two decisions. We can choose a 0 or we can choose a 1. For this bit, it is okay. But if it is not, if it is a 0, the highest bit is a 0, we have to choose a 0 instead of 1. Yeah. So this is one condition here. But the else condition is that if the highest bit for this limit is 0, we just need to update the current. So current is going to equal to current.children with this n. So if this n is 0, so it's current.children going to be 0. For this node, it's going to be 0 because 0 XOR 0. This value is just inside of the trie. This value is just our number enumerated from this value x. So this is just the highest bit. Yeah, we just need to check if this bit is 1. So for its children, it's going to also equal to 1 because 1 XOR 1 is going to be 0. If this bit is 0, so this n going to also equal to 0 because 0 XOR 0 is going to be 0. So this means if the highest bit is 0, so definitely we just need to find its children. Yeah, we just want to make it the same bit 0. Yeah, but if it is not, what are we going to do? Yeah, if it is not, we need to check if current.children with this yeah, we just need to check if we have it or not. So in our example, if it is 7, okay, so for the next bit after the XOR calculation, we want to get a 0. If it is okay, we can get a 0. Otherwise, we're going to continue to use a 1, but we will not count it. But if it is a 0, we're going to count it. Yeah, and this 0 is dependent on on our current number. Yeah, so because for our current number, this n, it can be a 0, or it can be a 1. Yeah, but this n XOR this n gonna equal to 0. This is exactly what we need. So 1 XOR 1 gonna be 0, 0 XOR 0 gonna be 0. This is exactly what we need. This means we're gonna count it from here. Yeah. So let me just prepare a result. Gonna equal to 0, and from here we're gonna code it. It's gonna be current.children, and for this node n, yeah, because we can find it, we can find this node, and then we're gonna code it. Yeah, but sometimes there's no such node. We have to check it from here. So if not current, so we're gonna break the for loop. This means we don't need to check it, and finally we just need to return the final result. Yeah, so this is okay. If we just want to count it. Yeah, but what if it is just the same number? So for example, this is 1 and it is still 1. So we're going to continue to check the next number. So this is 1, this is okay. We're going to continue to check the next bit. Yeah, after the highest bit, we're going to check the next bit. Yeah, because maybe in next bit there's a 0, we're going to still need to count it. Yeah, we are not sure. So from here, we're going to update the current. So the current is going to equal to current.children. But inside, we're going to use this n XOR 1. So this means if this n is 1, and for here, basically we're gonna, this 1 XOR 1, it is a 0, but for here, this 1 x, yeah, if this is a 0, 0 XOR 0, gonna be 0, but this is 0 XOR 1, gonna be 1. It means, yeah, we're gonna go to the next bronze, it is a 1. Yeah, so this means this is a 0 bronze, but we're gonna go to the next bronze, and we're gonna continue to count, and we're gonna go count the next number. Yeah. So if it is a 0, okay, 0 and 0, 0 XOR 0 gonna be 0, okay, but 0 XOR 1 gonna be 1. But if it is 1, 1 XOR 1, 0, it is okay. Yeah, but this 1 XOR 1 it's gonna be 0. Yeah, basically if it is this is 1, I'm gonna go to 0. If this is 0, I'm going to go to 1. This is the basic idea. Yeah, because for here, definitely I'm sure it's gonna be less than the limit. It is okay. Yeah, but for here, I'm not sure. I'm gonna continue to update the current node. I think it's all about it, but let me just run it to check. It didn't work. This is a 12 and this is a 6. Yeah, I'm not sure what is wrong with it. It's really difficult to debug. So I'm going to check the children is none, going to equal to the trie node, and current need to current.children with this this n, and the current.code going to plus equal to 1. If this limit on right shift to I and 1, if the current dot yeah, I think I did some mistake. Yeah, it's current.children n. if this bit is 1, and if this n is 1, I need to find 1, 1, 0. Yeah, I think it is okay. I don't know. If I change it, definitely it's gonna be wrong. If I go to another bronze, yeah, I think it is wrong. But why there are so many pairs? Yeah, let me just copy and paste. So first of all, I'm gonna use the insert, and then I'm gonna use the I'm gonna update the result, and then divide it by 2. It didn't work. Yeah, it's still the same. Should I update the counter first before update the children? No. Yeah, it didn't work. Yeah, I think I need to check my submissions. For the first one, it is okay. No, it didn't. Let me just check my submissions. Why? Yeah, and let me check the definition. Yeah, I don't know. Yeah, maybe my search is not okay. Let me check. So here I break it. This n is the limit, and 1. If count.children n without gonna plus equal to count.children n.count. Yeah, and count gonna equal to count.children. Yeah, I don't know. It seems it's exactly the same, but I don't know which one is wrong. Yeah, it's really difficult. Let me maybe copy the search. Maybe my search function is wrong. Let me just comment it and just check this search function. Maybe my search function is wrong because it's so difficult to find. Oh, this means my search function is okay. So my output is 12. Yeah. So it is still 12. Maybe my insert is wrong. I don't know. Yeah, let me just uncopy the insert. Yeah, it is still the same result. It seems my insert and search is okay. Yeah, so this means definitely maybe here is wrong. I don't know. Yeah, it is still the same result. Yeah, so now what left behind? Oh, I found the problem. So yeah, my problem is that my counter I defined it as 1. It should be 0 from the beginning. This is why. Yeah, because for this counter, it should be defined as 0. I don't know why sometimes I make it make it wrong. Yeah, so the code is gonna be starting from 0, and then for each of the node, if I go through it, I'm gonna update it to 1. Yes, this is so difficult if I made it wrong from the beginning. Now let me just run it. Now as you can see it works. Now let me just submit it. Yeah, now as you can see it passed for all testing cases. And the only silly mistake is that while I'm preparing the counter, I prepared it as a 1 instead of a 0. And it takes time to debug what is wrong with it. But basically for the time complexity for this problem, it is 15 times n gonna be 2 times 10 to power 4. Yeah, this is why it works for this try 01 try solution. Yeah, I think that's all about it. Thanks for watching. See you next time.